This is not a talk about rational and rational tools, but I'm going to use it as kind of a little bit of a case study. So my talk's going to be a little bit of case study, how we use this stuff and why we use this stuff. A little bit going into maybe some more detailed examples of the technologies that Brian showed, and then a little bit about some new technology, some work that I'm involved in trying to do some standardization of linked data technologies at W3C, some standardization beyond the standards that exist there already. So what is linked data? Brian talked a little bit about this, but linked data is a very simple idea. It was written down in these 4 rules by Tim Berners-Lee. I think it was written down in about 2006, although the technologies that it's based on are significantly older than that. The basic idea is terrifically simple. We've got this, the World Wide Web, which has been probably the killer app of all of our careers, the killer app the like of which we've never seen before, which is primarily based on HTML over HTTP and is focused on web pages that human beings read. And so the basic idea of linked data is terrifically simple. If it worked that well for HTML and human-read pages, why wouldn't it work that well for data? So if you just replace the HTML with some kind of machine-readable representation of data and create the same kind of web of linked pages that we have in the HTML world, do the same thing with data, and you have some kind of interesting thing. So what do you have to do in order to make that work? Well, you need URIs for things. So everything has to have a URI. So all those UUIDs and all of the sort of proprietary or local ways that we had of addressing things, just replace all of that with URIs. And in particular, use HTTP URIs because they're the most useful ones. If I get some random URN:URI, I don't really know what to do with it except compare it with another one. But how I actually get any data is a mystery. If I have HTTP URLs, then I do the obvious thing. I do a GET, and I expect to get back some interesting information about that URI. And then it says, when somebody looks up a URI, use some standards. So HTML was really the secret sauce that made the World Wide Web that we know today work. Everybody used HTML, everybody linked the same way. So you could write processors that, you could write browsers, for example, that showed HTML and other processors that process HTML. If we're going to do things, if we're going to have the same kind of success with data, we need a standard for how people are going to represent the data. If everybody does it differently, we're not going to get nearly as much value as we're going to get if everybody does it the same. So RDF is the standard for representing the data. And I forget why there's a little star here. I think this was actually in the original. I think I just copied this from the original. And Sparkle is a query language, a graph query language for querying over RDF data. And actually, when I think about it, it's not obvious why Sparkle would be mentioned at this level. But as I said, I just copied this from the W3C website. And of course, the thing that makes all of this useful is the fact that things point to each other. If it was just a way of having addresses for records, that would have some level of value. But the fact that the records point to each other and build up a web is what makes the HTML World Wide Web interesting. And same thing on the data side. So the basic idea is extremely straightforward. It's not something that you can learn and absorb instantly. It doesn't require any kind of study. And it's not new, as I said. And there's a lot of great material out on the web. There's actually, if you want just sort of a starting place for a talk on why you would care and what people can do with it, there's a nice TED talk by Tim Berners-Lee. So if you Google for TED linked data or TED Tim Berners-Lee, you'll see his talk. And so there's a ton of stuff that's already been out there. This is a sort of a graph of linked data sites that exist today that are linked to each other. And I think the one in the middle, which you can't read, is DBpedia, which is one of the... And DBpedia started when somebody had the great idea that Wikipedia is a great thing, but it's mostly human readable. But it's got a whole bunch of interesting information about a whole lot of interesting things. So somebody wrote a program, and I should know the name of that somebody. Apologies for the inadequate attribution. But somebody wrote a program that just read the Wikipedia pages and created a machine-readable corresponding page for every Wikipedia page, and that's DBpedia. And then, you know, there are many things that are connected. They're not all connected. This looks a little bit like a star kind of arrangement, but it's really not. There's nothing. DBpedia was one of the first and one of the best known, so it gets sort of star billing in the middle, but there's really nothing special about it. It's just a straightforward web of information. And then, of course, the interesting thing, and some of the early adopters of this and some of the biggest contributors to this are actually governments. So the government, or a government problem, is we've got all this public data, and the good governments at least take their responsibilities for public data seriously, and they want to make that public data available to the public. So how do you do that? So RDF has really got quite a lot of traction with various governments, the UK government, the US government. Sorry, I can't tell you what, if anything, the Danish government is doing here. Publishing public information. Another big user is the scientific community. So, you know, how do you get scientific information? So once all that interesting sort of public and scientific information is out there, you can start to do lots of interesting things. And there are lots of, and again, this is something that you can Google, there are lots of very cool applications of taking this data and then doing interesting things with it. This particular one is sort of mashing up maps with sort of locally available RDF data about those geographic locations. But there's all kinds of interesting applications that have been done in the scientific arena and things like that. And I'm being sort of, you know, vague about this because it's not really my topic today. So what we've been doing in IBM is actually a little bit different from this. We've been using the same technologies, using linked data, but our focus has been to solve a different problem, which was sort of application integration. And so I'll tell you a little bit about how we got there and what that actually means. I'm always amazed when I come to these conferences that I meet so many people who have these kind of cool jobs in various kind of, you know, startups or consulting organizations where they get to play with technology because it's cool, because it's fun, because it's interesting, because it's exciting. You know, I work in an old-fashioned company where you don't get to do that. You know, you only get to play with something new if you've actually got a significant business problem and you've pretty much shown, you know, through trial and error that you can't solve it with the more sort of conventional, conservative stuff that we use every day. So this is my expression of our business problem. And our business problem was that we're a vendor of applications. You know, rationally you think of them as development tools, but you can also think of them just as applications. So we're a vendor of applications, and we have a suite of applications. There's actually over 80 products that Rational sells. And there's been pressure from our customers for a long time to make them work better together. So a typical customer conversation says, yeah, I know you can manage my source code, and I know you can manage my defects, and I know you can manage my requirements, and I know you can manage my test cases, but none of that is really my problem. My problem is I've got a development organization, and I want to have a development process for my development organization, and I want to be able to describe it all. So don't talk to me about them individually, talk to me about how you're going to help me solve my, my development problem. And so you can see from this data, which comes from 2008 from Forrester, that despite trying to integrate our tools for a very long time with all of the classic methods, and actually putting, you know, our customers don't always give us credit for this, but putting tens and even hundreds of millions of dollars of effort into those integrations, they're still not good enough. And part of this is, part of the reason is that we haven't done a good enough job with the tools that we had available, and part of it is that our customers' environments are very heterogeneous. So they typically have a little bit of IBM and a little bit of, you know, various other sort of vendor products and stuff that they built themselves, and so making it all work together is a fairly, you know, remains a fairly significant challenge. So even if we were doing a perfect job ourselves, which we're not, there would still be an interesting problem. Now, is this business problem unique to, you know, my situation as a, you know, as a commercial vendor? No, it's really not. You know, all the commercial vendors of software in all domains have this kind of integration problem, and it's a very relevant problem for a lot of sort of standard large enterprises almost every customer in every industry that I talk to has some kind of 360-degree view of the customer kind of ambition. So if you're a bank and you do retail and investment banking and maybe you're tied into insurance as well, you want to tie everything together. Or you're a telco and you sell cable television and telephone and network access. So people, regardless of the industry, people are trying to sort of tie things together. So I think that this kind of integration problem is actually key for many people. And I actually believe that there's more interesting value to be had in integration than in building new things. We've been building new applications for a long time, and there's no shortage of sort of interesting mousetraps for building applications. And there's no shortage of people coming year after year with new mousetraps for building applications. So the actual building of applications, terrifically important, of course. That's the building bricks for what we have. But actually making them work together in some kind of coherent system, I actually think is a problem where there's more interesting business value to be had, perhaps, than in building sort of new isolated kind of things. So how have we done application integration in the past? And again, I've expressed this as in using the example of tools from our domain, but I think you could substitute another domain without difficulty. Well, there's two main models I contend, or I assert. You can contest it if you like. But I think there's two main models that people have worked with for probably as long as I've been working. And one of them is the standard sort of API model, and we've sort of formalized it in different kind of ways. Service-oriented architecture is the sort of is a marketing term that recently has had some success in describing this model. And it's pretty straightforward. You have all of these kind of applications, and each one of these applications opens up an API. So my little kind of socket diagrams are designed are attempting to symbolize those APIs that get opened up by these applications. And then you write a bunch of glue code for tying them together. And sometimes the glue code is in one application using the API of another application, and sometimes the glue code is in some third place, sitting on some enterprise service bus or something, doing these kind of things. But it's basically sort of APIs and glue code. And the actual data that's stored in the applications is kind of relevant, it's important, but it's a secondary kind of thing. The first thing is my application's the center of the universe, with its API being its public face. And the data that I hold, that's my data, right? So it's there, but it's not primary. And actually the way that you address these things is typically very variable. Each API makes up its own way of how you actually address the data that's behind it. This is a chart. I found this chart. This is an IBM chart from around 1990. So 22 years ago. Everybody already knew that model, this model has actually been successful and is still the dominant model, and it's actually delivered a lot of value. Everybody's done it, both in the industry that I work in, but in many others as well. And it sort of adds value and it gets you so far, but it's pretty unsatisfactory in different kinds of ways. Where we never have enough glue code, we never have enough APIs. Every time you update the versions, the APIs change and the glue code breaks. There are many sort of issues with it. And so the other big idea that people have had forever is if we could just get all of this data in one database. Sometimes people prefer to call it a repository rather than a database. If we could just get it all in the database, all of this difficulty would go away. Everybody would all put the data in the database, then you could query over the database, all kinds of good things would happen. And IBM had a project called AD Cycle in 1990 that tried to do this, and many others. In fact, there's still many vendors whose that's their basic strategy. We could just all get it in our database or our repository, everything would be good. And it doesn't really work, right? Because it doesn't support heterogeneous environments. What do you do if you go into a customer organization and they've got stuff from all over the place? What do you do with legacy stuff? It's a big sort of Soviet planned economy kind of view of the thing. It sort of assumes that I can manage this repository and I can manage its schema and all of these kind of things. So there's many reasons why this model has failed for decades and will continue to fail as long as people try to do it. But those are the two basic sort of strategies that we've sort of flip-flopped between or tried to combine in various ways for the last sort of 20 or 30 years. it might be a little bit interesting to look at what does actually mean integration? What are we actually trying to make happen? Well, in our world, you know, one of the things you're trying to do is you're trying to create links between artifacts and different tools. So I've got a test case, and that test case validates that a particular requirement on a particular piece of software is satisfied. So I'm trying to make a link between the test case and the requirement that it satisfies, or something like that. Often within one tool I need to be able to create an artifact in another. You know, the build runs and a bad thing happens and I get some kind of debug information out of the build, right? I was running a test case, the build failed. I'd like to open a defect, right? So the build engine, there isn't a human being who can sit there and type it out. The build engine wants to automatically create a defect, and that defect has to be in a defect management tool. And sometimes I just want to select. So this was really, there was an existing requirement, I wanted to select it and join it to the test case. In this case, there was no existing defect. I wanted to create one and tie it into some kind of test failure record or something like that. I'd also like to share common concepts. That's one of the integration things that you want to have happen is that it's not just that the tools are separate and you want to integrate them, you actually want to combine things. So we all, you know, I've got testers, requirements, people doing defects, people doing source code. We all kind of know that we're working on the same product, and that product has certain releases. So there are certain of these kind of central pieces of data that you'd really like to share, and we've never been good at that. You know, what actually happens is right from the beginning you install the tool, and then you define a set of users in this tool, and a set of users in that tool, and a set of users in the next tool, and you create a project in this tool, and a project in that tool, and a project. So there's a whole bunch of sort of shared stuff that we're not good at. You want to be able to query, which was one of the reasons why people were so drawn to this kind of central repository kind of thing. So my sort of sample query from our domain, again, not hard to imagine in different domains, my sample query from our domain is, give me a list of all the new test cases that I should run on last night's build. So that's not, that shouldn't be very complicated, right? I know what the build was, I know what change sets went into the build, I know what defects or requirements that those change sets were related to, and I know what the test cases are for those defects or requirements. So good old-fashioned sort of relational join across 4 tables ought to be able to get me the answer, show me all the new test cases to run on last night's build. But in fact, has been relatively difficult to do in practice in this kind of heterogeneous kind of environment. So that's some of the things that we want to get out of this. So having spent a long time and a lot of money getting as far as we could with those 2 old ways of doing integration and lots of variants that we thought were new but which were, when you really looked at the essentials, really weren't so new, were really the same. We've been working for about the last 5 years in Rational on something that we think really is new. And it's not something that we invented, it's something that we just sort of latched onto as, here's a new way of looking at the problem. And maybe if we try this, we'll get better results than we did before. And in this one, which looks a little nicer on my screen than it does on here, there are actually some tool-like things here. The first point is, so linked data is the new idea, right? So if you'll pick up on this linked data idea and apply it to our domain. So what would it look like? Well, the first thing is, you sort of forget about the tools. If we've had so much trouble integrating these tools and managing the APIs on the tools, how about we just get rid of it, right? If that was causing so much trouble, let's just not have APIs on tools. And instead you flip the whole thing around and you say, the important thing isn't the tools, forget the tools, the important thing is the data. So all of those kind of builds that were hidden inside the build tool, and the source code that was hidden inside the source code management system, and the defects that were hidden inside the defect tracking system, bring those out as the primary things and forget the tools that are behind them. You give them all URLs, so we do the linked data thing. Every one of those artifacts has a URL. The relationships between them are trivial, right? If you want a relationship, you take the URL of this one and you stick it in this one. So A points to B, just the way we do with HTML, right? You put the URL of one page in another page. So you do the same thing at a data level. And actually, I did actually mean for this chart to put the tools in the background, but I actually overachieved on that, so the tools you actually can't see here. But the message is that, the tools really are there, but they're sort of hidden behind the data. They're not really terribly important. They just support the data, and the data is the primary thing. So kind of a different way a different way of thinking about the problem. So Brian's already talked a little bit about RDF, but I first learned about RDF a long time ago, probably, well, I say learned, I first came across RDF a long time ago, maybe about late 90s, 1998, 99 or something like that was the first time I came across it. And I really didn't get RDF at that point. I sort of looked at it and I said, yeah, that looks very familiar. You know, it looks like very similar to the object-oriented. I was a Java programmer at that point and had been a Smalltalk programmer for a decade before that. So looks a lot like objects, you know. RDF looks like the data that I hold in my objects. You know, it's done in a name-value pair. And this RDF schema stuff looks a lot like class definition. So I completely, even though I saw it and read it and even played with it, I completely failed to grasp it. So that's why I think it's actually worth me reinforcing a little bit of some of what Brian said. So it serves as this kind of universal data representation. You know, it is to the data on the linked data web what HTML is for UI presentation in the human readable web. It is a lot like name-value pairs. Well, in fact, it contains sort of name-value pairs. But RDF adds this idea of a subject. So instead of just saying property 1, value, value whatever, property hair color, value, in my case, white. Didn't always used to be that way, but that's how it is these days. It adds the notion of a subject. So I have a complete triple that says Martin Nally hair color, white. Right? So sort of a self-contained thing. And that turns out to actually be quite fundamental. And it makes much more change than you would think it would do. So I'm going to give a little forward reference here. One of the surprising results of this is that if you have subjects, a whole lot of other things that you thought you needed go away. So we were, previous to working with RDF, there was a lot of people in IBM, still are actually a lot of people in IBM, who really liked Atom Publishing Protocol. Right? So Atom Publishing Protocol gives you these kind of entries, and you post entries to create lists and stuff like that. It turns out if you have subjects, you don't need Atom Publishing. So there's a very surprising relationship. You wouldn't think that there would be any relationship between those two things, but there is, and I'll explain that a little bit later. It's extremely simple. RDF itself is extremely simple. It's just these triples, subject, predicate, object, and you put them all in a graph. And in the case of linked data, the graphs that you're interested in are the actual resources on the World Wide Web. So you've got these resources, and when you do a get on these resources, they're full of these triples. And that really is all you have to know. And one of the reasons why I think RDF has gotten off to a very slow start is it went through this sort of trajectory of a lot of people who were interested in more advanced use cases. They're interested in inferencing, or they came from an AI background, sort of grabbed on this, and it sort of got caught up in a lot of hype around the semantic web. And I think a lot of practical people sort of instinctively shied away from that. And a lot of people took a look at it and said either they said, as I did, oh, it just looks like the stuff I've been doing anyway, so there's nothing really new here. Or they said, this looks like a lot of artificial intelligence warmed over, and it didn't really work out the first time, so I'm not going to trust it the second time. So I think a lot of the way in which RDF... So my point here is, it's terrifically simple, and it is actually quite different from what we've been doing before. And I'll try to explain that a little bit more. So RDF just looks like... So here's my example, right? Supposing... Is there a pointer? Do you have a pointer?
I have one.
Can I borrow one? I have short arms, so I just point in the meantime. So up the top here, imagine that this is a resource.
I'm assuming this isn't going to need a driver.
No,
it needs laser.
Yeah.
Oh, laser pointer.
Yeah, I'm just looking for something. So imagine this is a resource on the web, right? So it's a resource with an HTTP address. It's just r1 example.com as the host. And imagine that this is its representation, and ignore the prefixes. They're sort of like XML namespace declarations. They're not terribly important. They don't really have any significance. It just avoids writing long screens. This is that sort of thing that you see on the airplane when you say that this movie has been reformatted for your screen. Well, this is just, the prefixes are just reformatting for the screen so I can make it all fit. But the way that triples work is they're just, the subject is always an ID. It can be a URL, and then they have these kind of little sort of internal IDs for sort of embedded things that they're really just, they're like URLs, but you can't see them outside the graph, so they're not addressable outside the graph. So you have an ID, which is usually a URL. You have a, this is a URL too, and it's sort of disguised by the fact that I created a prefix because I couldn't make it fit on the chart otherwise, right? So that's the only reason. So this is just a shorthand way of writing the URL, which is this RDF URL with type appended on it. And then same with the object. Now the object can be, in RDF, you know, actually RDF doesn't really say what the types are, but by convention people use the types from the XML schema part 2. So you have strings and booleans and dates and things like that. And then of course the other interesting data type is the URL. And that's how you do links, right? So pointing to something else, right? So terribly simple. So this is my link data resource, and this is its representation, which is just 3 triples. And you'll notice that the subject triple happens to be in this case the same as my link data resource. So this link data resource's representation has information about itself, 3 pieces of information about itself. And this kind of pattern where the subject of the triples, oops, no, I'm in trouble with the pointer. This kind of pattern where the subject of the triples is the same as the resource that the triples live in is a very common pattern. So that's the thing that you see sort of 90% of the time. And here's another one. I did some reformatting which didn't work out. Here's another one that's kind of similar. It's a second resource. This is TC1. It has some information about itself, including a reference to another thing. So this is my test case test this requirement kind of example. So you know, we know how to represent this. So this, and you can see why I didn't get this the first time I saw RDF, right? Because this just looks like the stuff we always do, right? You know, I have one object called R1. I have another object called TC1. I've got properties and property values on each side, and one of the property values represents a link going from one to the other. So it looks like nothing new, right? But because RDF has these kind of the ability to hold its own triples, I can do this example, which is different. And in this example, the actual resource, which I'm not failing to point to, but the actual resource is not TR1 or TC1. Actually, it was R1. Oh yeah, not R1 or TC1, right? So it's some completely unrelated resource. But it has information about the first 2 resources. It has information about R1 and information about TC1, including that link that I just had. So this is actually kind of a bit different. So how would you represent that? I'm not even really sure how to draw it. You know, I just kind of drew it. I've got these 2 resources, and they've got the reference between them, but the resources themselves are actually empty. They don't know a thing about themselves. I've got this other resource, and the interesting thing is, I have no information about this resource, but within this resource, I have information about the other resources. So this is kind of a different kind of paradigm, and it turns out to be a very useful one. And it turns out that you can do lots of interesting things. So let me give you one example of something that we do. And actually, I wish I had, remember on this version of it, I wrote sort of validates here. So, and of course, we know from the previous example that the information is actually stored here. So this test case validates this requirement. Now, you know, in lots of design examples, it turns out that that's not the most interesting place to put it. It may be that because of my sort of use cases, because of my access patterns, it's actually much easier if I hold the relationship on this side, right? So in object-oriented programming, what would you do? You would change this predicate. Instead of saying validates, you would say validated by, and you would put the information over here and put the pointer going backwards, right? So we're all very familiar with that. You can do that in RDF, but it's probably not what you would do. In RDF, what you would do is you would just take the triple that was over here that said this test case validates R1, and you just take the triple the way it is and move it over here. So you don't have to reverse the predicate just because you want to store it over here. You can store the triple wherever you like. It can be here, it can be here, it can be in some third place. You don't have to do these kind of, invert the relationship just because I find the need to store the relationship somewhere else. Which might seem like a small thing, but when you start thinking this way, it's one of those kind of things where you just kind of think different. Here's another place where I absolutely didn't get it, is with RDFS and OWL. So RDFS, which is the RDF schema stuff, introduces classes and properties. But they're not the same as the classes and properties that you know from object-oriented programming. And they're actually not the same, they're not really analogous to sort of table definitions and column definitions in relational tables either. And in fact, they pretty much in every way work backwards from the way that you're used to. In object-oriented programming, you declare the classes first, and then you create the instances of them. In RDF, you work the other way. You create all the instances first, and then you worry about what their classes might be. In object orientation, we're used to the fact that everything's an instance of one and only one type. In RDF, an instance can be a member of as many types as you like. It's not or none at all. There's no particular sort of hard-coded relationship. In object orientation, we're used to the fact that classes constrain instances, right? So if you're a member of this class, then you must have a hair color and a name and a title and things like that. RDF is all about working the other way. RDF says, if you have this characteristic, then you must be a member of this type. Not, if you're a member of this type, then you must have this characteristic. So it's sort of, A implies B is not equivalent to B implies A. So RDF and OWL have these kind of class things, but they're all about B implies A. They're not about the A implies B that we're used to. And it's quite challenging. My experience over the last 4 or 5 years working with some quite smart engineers within IBM is that getting them to realize that RDFS and OWL classes are completely the opposite. Everything goes in the opposite direction from what they're used to is actually quite a hard transformation to make.
Some forms of OO.
Yeah, some forms of OO.
Many forms of.
Yes. Okay. Well, maybe you can follow up on that later when we have this other question and answer. So, but certainly the skills and understanding that the vast majority of the developers that I work with, this is true for. People who've worked in Java, they worked in C++, they might have worked in Smalltalk or other kinds of things. They have a completely backwards. They have completely the opposite view of the relationship between classes and instances from the one that is in RDFS now. I'm pretty excited about this, right? So there haven't been a lot of changes. I got excited about object orientation when I learned Smalltalk back in the late 80s. So I was a sort of mid-level adopter, not a super early adopter. And that was a big change. Going from client server to mainframe was another big change. Starting to think about the world this way and starting to do application integration. Think of the World Wide Web, think of data as being primary, thinking of data as being sort of addressable HTTP resources on the web. Really is quite an interesting new way of thinking about the world. The first one that I've been excited about in a while. So what have we actually done with this? We have in Rational, and currently almost all the integrations between Rational tools are implemented with linked data. There are a few sort of stragglers that are sort of older that are not done this way, but pretty much everything now in Rational when we're integrating things is done this way. We created an open community to share specifications. There are about 40 companies, including IBM, that are working on these kind of, simple. It actually turns out to be useful to have a little bit of, if you're trying to integrate test cases with requirements, it is actually useful to predefine some of the useful sort of predicates that are useful properties, if you like, that are common to pretty much everybody's notion of what a requirement is and pretty much everybody's notion of what a test case is. You don't want to overdo that because we're not trying to specify what a requirement system should look like or what a test case system should look like. We're just trying to focus on those predicates that are useful for integration, which is really a small subset of what any system would do. We started working, which I'll talk about in a moment, we started working with the W3C to start a work group for linked data focused on standardizing some patterns that we think are important. Some typically and rational integrations are currently on linked data, and some rational tools are actually built on linked data top to bottom, all the way from their storage all the way through. It's all sort of RDF end to end. Others of our tools, usually the older ones, you have some kind of internal format, probably a relational database or something else that they're using for storage, and they're only using the sort of linked data stuff on the outside as an integration sort of layer. So there's a problem with all this. Despite the fact that we've had significant success and we're extremely excited about the direction, we acknowledge that there's a problem. Most of the experience with linked data that you can Google on the web is about read-only linked data. It's about a whole bunch of public records that were created somehow, you know, unspecified, and then exposed as linked data, or scientific information that was created somehow and stored somehow and exposed as linked data. If you're doing application integration, it's really a read-write problem. It's not a read-only problem. You have to be able to create things, you have to be able to create new links and things like that. So it's a read-write problem. And there isn't much of a body of knowledge on how to do read-write linked data. Now, what it actually turns out to be closer to the truth is that the information that you need is there, but it's scattered all over the place. You know, there's a little bit in this spec and a little bit in that spec, and knowing what to select and put it out, how to put it together is really the problem. It's not about inventing a whole bunch of fancy new technology. And here are some of the things that you run into. You know, it seems obvious that you post to create, but what do you post to? And how do you find links? How do you find lists of things that are already there? And how do you deal with media types? And what about binary resources that I can't represent in RDF? How do I stitch those into the web of data? And you know, what should I use for primitive types, since RDF says use whatever you want? You know, and clearly, if we all do that and we all pick something different, then we're not going to get the interoperability that we want. And blah blah blah. Standard vocabularies are actually very important. So you know, actually somebody was asking Brian at the break, you know, what happens if I want to do a query across things and somebody used FOAF name and somebody used, you know, DBpedia's version of name for a person? You know, how can I query across that? Well, there are answers for how you can query across it, but the best thing is if we just all use the same words in the first place. It's a little bit like human communication. Yes, you can bridge across different languages. In fact, you know, my job in IBM is working with a whole bunch of teams, and you know, I'm not the chief technology officer. I'm the chief translation officer. You know, my job is to go around the different teams and teach them that, you know, that word that you use and you think that it could only possibly mean one thing. Well, actually, over here it means something completely different. And for the idea that you were trying to express with that word, they use this other word, right? So yes, you know, having a chief translation officer is useful, but it's even better if we all actually use the same words. Some other things. So the solution, the good news of the solution, as I already said, is that in general there already exist simple answers to these questions. The bad news is nobody knows what they are, or at least there isn't common agreement on what they are. So the action that we took is we started this new W3C working group. IBM made a submission along with some other companies. And so there's now a working group aiming at creating a standard called this linked data platform, which is standardizing these conventions for how to use linked data in this read-write kind of way. And you know, please look it up, and if you're interested, come join, come help. So the IBM submission, should I call it the IBM submission? I think it was actually, technically, we did actually write it. But it was a sort of, subsequently we got some support from some other companies, and so it was presented as a joint submission. So my apologies to those other companies if I'm diminishing their role in the process, not my intention. It's not really important whether it was an IBM submission or not. The submission that started this work group defined something called a basic profile. And we called it a basic profile because we were trying to emphasize the fact that it's mostly not about invention, it's about sort of profiling, selecting existing technologies and showing how to use them. We made the observation that sort of 90% of all applications are just records and lists. This has been true since I've been working. And it's not changing really. You know, records and lists are not unique to relational database. They were around prior to relational databases. You know, hierarchical databases are often sort of trying to express records and lists. And if you look at what people do with the newer, trendier sort of NoSQL kind of stuff, they're often dealing with sort of records and lists. So if you can figure out, if you can describe to people how to write a linked data application that deals with records and lists, you've actually you haven't solved all problems, but you've solved a surprisingly large number of problems, because a surprisingly large number of applications are interesting variants on records and lists. So that's exactly what the submission at work at W3C sort of focuses on. And there's an interesting sort of comparison here with Atom publishing. And as I said, prior to the work that we've been doing with RDF, there's a lot of people in IBM who are using their XML-centric, and they think that Atom publishing is a fine way for them to express lists, which is one of the things that they need to be able to express. And actually, if you're coming from an XML perspective, I actually believe that Atom publishing is a fine way to express lists. But if you're coming at from a linked data perspective, you find that it's actually not, Atom publishing is not terribly interesting. So I'm going to talk a little bit about Atom publishing, partly because it's a useful sort of comparison point. There's nothing special about Atom publishing, it's a useful kind of comparison point. And also because I have a history of arguing with people in IBM who wanted to use Atom publishing and who thought that I should be using it too. So, two motivations there. How many people know Atom publishing, XML? About half the room. Half the room put up hands, that probably means 3/4 of the room actually knows it, and only half of them actually volunteered information. So Atom's pretty simple. Atom says, you know, we understand that collections are important, so we're going to have these collections, we'll call them feeds. Actually, they're sometimes, I'm not actually sure what the official thing is. The actual tag is feed, but the word collection is actually used in the Atom publishing spec. So the idea is I'm going to have this resource on the internet, which is a feed, right? And I'm going to add entries to that feed. So the feed of the collection is an HTTP resource. And the way that I add a new entry is I post it. So I post this thing called an entry. So I made up two concepts. I make up the concept of a feed, or a collection, and I make up the concept of an entry, and then I make up some other things, some standard predicates and things like that, and a MIME type, which I also make up. So there's a fair amount of invention in Atom publishing. I'm not trying to bash Atom publishing, but there's a fair number of concepts that get invented and get documented. But the basic idea is that I post a new entry, and once I've posted a new entry, it'll show up as an entry in my feed. So if I do a get on the feed, I'll see the entry that I posted, and the entries themselves also have their own URLs, so I can do a get on the feed, or I can do a get on an individual entry. So a pretty straightforward idea, and actually terrifically useful. How many people have actually found value in APP and actually used it to solve real problems? Yep, several of you. I'm not in the least surprised. It makes total sense if you start from XML as your perspective, if that's where you start. So when we talk to them, talk to the APP people, they say, we know all about how to accommodate you, because the content type in Atom is open. So just stick your RDF stuff here. You guys know how to represent RDF in XML, right? It's a fairly unnatural act, but you can do it. There's a spec called RDF, for RDF XML. So just stick it in here. Well, you know, we're not really very happy about that, because what that means is that if you're going to read this kind of stuff, anybody can read it so long as they understand. So long as they're a piece of software that understands both RDF and Atom. Well, how many pieces of software like that are there in the world? The answer is 0, right? So, not really very attractive. So then they usually make, okay, second offer. We will represent the Atom part itself in RDF. And here's what it might look like in Turtle. And I don't know how much Turtle you showed. Turtle's actually a little bit misleading. Actually, so is RDF XML. Because in RDF, there's really only two concepts. There's these triples, and then there's the graphs that the triples live in. And that's it. There's nothing else. There's no nesting. There's no fanciness. There's nothing. It's the most brutally simple data model that you can imagine. But the syntaxes that have been developed to make it easier and more convenient to express this thing actually look as though they're providing more structure than actually exists. So it looks, for example, as the stuff that's in these square brackets looks like a little sort of nested object. There are no nested objects. It's just a convenient way of grouping triples together and giving them a common subject. And the parens are defining an RDF list. And an RDF list is really just a structure that's built out of more primitive RDF things. It's not really built into RDF. It's a sort of an example of something, a standardized pattern, if you like, of usage of RDF triples. So the syntaxes unfortunately make RDF look as though there's more there than there really is. And actually one of the things that you should do when you get a piece of RDF is run it through one of the validators that just maps it out to the triples, because that's really the reality, is those triples. But anyway, you can imagine something like this. And, you know, I feel sorry for the APP, or I feel bad about the APP guys within IBM because they're really trying hard to accommodate us. And still we look at this and we say, that's not really, you know, thank you for trying so hard to be nice and accommodating us, but that's not how you design with RDF. When you have RDF, you just don't think that way, right? You know, we don't really need your entries and your feeds and things like that. We don't really need custom media types. You know, it's all, if you just use RDF, you don't need that stuff. Okay, so how do you design with RDF? Okay, so we still need collections. You could use RDF seek or list, but those also have their own sort of issues. They're not very query friendly and things like that. So, but you can go back to more basics, right? So we have these triples, and the triples, and again, unfortunately I used a little syntax here. In turtle syntax, it gets tedious to write subject, predicate, value 1, same subject, same predicate, value 2, same subject, same predicate, value 3. So it's tedious to write, although that's really what the underlying model is. So turtle lets you have this abbreviation where you write the subject and the predicate once, and then you just put commas between value 1, value 2, value 3. So it's not implying any kind of interesting structure or anything like that. It's just a shorthand for giving the triples. But if you do that, you naturally define a collection. Because if you take all of the triples that have got the same subject, the same predicate, but different objects, voila, you have a collection. So if you're doing this in a linked data style where you're trying to combine HTTP with RDF, then what you do is you just say, well, a collection can be any resource. I'm going to post to that collection and it will do two things. The post will create a new resource, and in addition, it will add a new triple with the same subject, the same predicate, and a new URL, a new value, the new URL being the URL of the new resource that I just created. So collections kind of are already there. You just need a little bit of a pattern, a little bit of a convention on how to do it. And if you do a get, you know, you'll get back the list of the existing ones, which is pretty much what APP gave you. So a basic writable correction. Here's an example. You know, here's one. I've already posted two things. The collection that I'm using, or at least the subject that I'm using, is this sort of collection 1. Imagine that that is actually the URL of the resource that it's contained in, and RDFS member, which is just a handy predicate that happens to be around, because we don't really like making up predicates, right? Because if we're all making up predicates, we can't talk to each other. So the first thing that you do in the RDF world is that if you need a predicate, you go hunting for one that already exists in one of the standard published vocabularies. And I chose RDFS member. But you can use any predicate you like and play the same trick. But you object. APP, as a publishing protocol, actually does much more. Right? So it's much more interesting. It does more than that. And in particular, one of the nice things, if I do a get on a feed, I get information about each one of the entries. So you saw the different sort of the XML that sort of gave me. So that's actually a lot better, because if I do a get in the feed and all I get is the URL of the entries, and then I have to do a get on each one of those URLs in order to get information, it's going to take a long time for my list to actually appear in a user interface or things like that. I'm going to have problems with network traffic. So it is very valuable. What APP does is that in the feed, you have interesting information, interesting property values from the entries themselves. That's what allows you to have a blog be immediately display fast or something like that. Well, if you want data about the entries, you don't really need to invent anything in RDF. You just put it there, right? So let's look at an example of that. So here's my same resource. Here's the collection. I've got my subject URL, my predicate URL, and the different values that define the collection itself. And then I can just start adding triples that give me information about these elements. So first element, I can just add first element, predicate 1, value 1. You know, predicate 2, value 2, predicate n, value n. And then through to last element, I just put predicate 1, value 1. So whenever you want information about the entries, I just add more triples, right? No need to actually invent anything except that convention, that pattern of having done it. Kind of interesting. I didn't need a media type. I didn't need an entry concept. Nothing like that. So I just used what was there. There is actually a tiny problem that I'm glossing over here. Is that if this representation is going to have lots of triples with different subjects and different predicates, how can I tell which subject and which predicate is actually defining the contents, as opposed to just giving information about the entries? And we provide two answers for that in the work that we submitted to the W3C. One is just convention, is that barring any other information, we'll assume that the subject URL that you're using is the URL of the collection itself, and we'll assume that the predicate that you're using is RDFS member, because that's the kind of generic membership triple. And if you don't want that, then you have to tell us otherwise. And so that we invented two new predicates that you can use to tell us what the subject URL and the predicate URL for the collection are if you're not using the default. We give you a membership subject and a membership predicate. And actually that's the first thing that we invented. So we got quite a long way into Atom publishing without inventing anything, just telling you how to use what was there. And then we finally had to break down and invent two predicates. And in fact, the whole submission has maybe, I don't know, half a dozen predicates in it. The submission is actually longer because it tries to explain what's happening and explain the motivation and explain the backup, explain the background. But if you actually took the technology of the submission, you could write it on a page. You know, so it would be, you know, at least one order, maybe even 2 orders of magnitude smaller than the Atom publishing spec. So it's you could write it on a card probably. So APP actually has a little bit more than that even, because APP also covers sorting and pagination. And it turns out that there are equally trivial answers, or equally, I don't know if trivial is the right word, but the answers to those are also already there. You just have to see that they're there in the case of RDF. And I won't go through those in detail. If you're interested, you can go to the link that I showed you, and you can see how we propose at least. And maybe there are better examples. Maybe when we've gone through the work group at the W3C, people will have better ideas of how you can do these kind of things using what's there. But you know, you can see the ones that we pointed out are already there and which appear to kind of solve the problem. Yes, and so we sort of end up. I mean, this is the sort of summary of the whole submission. You know, RDF already knows how to do what you need to do. You just have to know how to do it in general. So that's the list part, right? So I haven't actually talked about the resource part, but it's very similar also. You know, that's how you make lists. Well, what about the resources? How about those other things that I talked about? What media types and things like that? Also, have I run over? Mm-hmm. Okay, sorry about that. Well, I can just be done at that part. So that's the work that's happening at W3C. Come join if you are interested. And if you get any other questions either about the technology or what we've done with it in my group, I'm happy to answer questions on that.
Thank you.